We now know a great deal about how to construct a voltaic cell. We know about anodes, we know about cathodes, we know about oxidation and reduction, we know about winning electrons and losing electrons. So now we're ready to do some very important calculations. We also recognize that we can write the cell voltage for non-standard conditions in terms of the cell voltage under standard conditions and the quantity Q, which is the reaction quotient. And we deduce that from the Nernst equation, which is what this equation is, and that means that our cell voltage under non-standard conditions is equal to our cell voltage under standard conditions minus RT over NF times the log of Q, the natural log of Q, where R is the gas constant, T is the temperature in Kelvin, N is the number of electrons involved in the overall process, and F is the Faraday constant. So let's suppose we set up a voltaic cell, which is also called a galvanic cell, that engages the two reactions involving the nickel cation, nickel 2 plus, and the chromium cation, chromium 3 plus. We can look up in the table and deduce the fact that the standard reduction potential for the nickel electrode is minus 0.25 volts, and the same quantity for the chromium is minus 0.74 volts. So we can immediately set up our little sketch, which we always do for any voltaic or galvanic cell we're going to build. And we know that we've got an electrode that is immersed in a solution on both sides. And we also know that when we look at the standard reduction potential, we can immediately tell which of those electrodes is the cathode and which one is the anode, because we know that the cathode has the greater standard reduction potential. And in this case, the nickel electrode sits higher in standard reduction potential than does the chromium one. So we know that the Ni2 plus is going to be the cathode. It's going to be the winner of electrons. So we know that we have nickel 2 plus on the right-hand side, and we've got chromium 3 plus in solution on the left-hand side. We know that this is going to be the cathode because it's the winner of electrons, and we know that this is going to be the anode, which is the loser of electrons because oxidation occurs at the anode. So when we connect our wire, we know that our electrons are going to go from the anode to the cathode. So electrons are going to flow in this direction. And we also know that the minute those electrons flow, we've got to balance the charge with our salt bridge. So we add our salt bridge in that maintains neutrality charge-wise in those two solutions. So we want to calculate this cell potential when the nickel cations are 1 times 10 to the minus 4 molar, and the chromium cations are 2.0 10 to the minus 3 molar. Now you recognize immediately that these are non-standard conditions because standard conditions are unequivocally 1 molar for each of these solutions. So that tells us very clearly that we have to use the equation for the cell voltage under non-standard conditions.